So we started the hour with that. And now we're going to do some bookkeeping. That's not all of it. I think there's about 11 of those across there. But I want to take this compound, and I want us to run through and answer these questions. Okay, on this one, and in your lab manual, it puts a lot more. It says here, number of atoms directly bonded to the central atom. Okay, so here, how many atoms? 2. How many atoms bonded to the central atom? 1, 2. And if that had been a double bond, it's not an extra count. It's how many atoms. And I don't care if it's a single, double, or triple bond. We're counting atoms. Okay, how many lone pairs on the central atom? None. Okay, this column right here is the sum of those two. Now, number of things does not sound very scientific, but it's better than what they say. In your textbook, this is what they call it. They call it areas of high electron density. Okay, I don't think that's very descriptive to help you. I think things work better. And the things are the sum of those two things. Okay, now this is veering into chapter 8. Let me see if I have my toys. And this is where I get to tell cat stories. We are moving into, actually, to talk about molecular shapes. And in chapter 8, there are 2 major theories. Don't bother to write this down. There are 2 major theories that help us predict what a molecular shape is in 3-dimensional space. The first one is called this: valence shell electron pair repulsion theory. A mouthful. Valence shell electron pair repulsion theory. They usually say this. If this were a word in English, you might pronounce it VSEPR. And so this is the so-called VSEPR theory. Valence shell electron pair repulsion theory. That is the one we're going to use about 90% of the time for this chapter 8. A second one is the valence bond theory. What your authors do in chapter 8, I find, is horrible. They take a molecule and they say, let's use the first theory, and then let's use the second theory, and by that time you're totally confused. So what I'm going to do, I'm going to go through the entire book, not today, but the entire, I should have said chapter. I'm going to go through all of chapter 8. We're just going to use the first theory, the VSEPR theory. Then we'll go back and spend just a little bit of time on this second theory called valence bond. They both lead to the same structure, but from a different point of view. Okay, now, back to beryllium chloride. It has 2 things around the central atom. This is the VSEPR theory. Okay, cat story. Back in the days when I only had 2 cats, okay, actually right now I have 5, but if it's worth doing, it's worth doing to excess. But back in the days when I only had 2, here's the premise. The cats love me, they hate each other. Okay, so when I come home at night, both cats come running toward me. Okay, they want to be as close to me as possible. Okay, so cat number 1 comes over and sits here on my right-hand side, and I can reach down and pet her. Okay, cat number 2, she wants to be close to me, but as far from her sister as possible. Where should she sit? The other side. Perfect arrangement. because that's as far apart as they can get. That is the cat repulsion theory. Okay? So, what you have here, the orientation in space, okay, cat, person, cat. What's that bond angle?
Linear.
It's called linear, but what's the angle? 180. Okay, so guess what? I'm a beryllium. The two chlorines love me. They hate each other. Okay, one chlorine here, one chlorine here. They're getting as far away. Each thing around the central atom wants as much turf for itself as possible. So, what is the orientation for this is linear. And if we do not have lone pairs, that will come later. If we do not have lone pairs on the central atom, these two answers will be the same. And then we have bond angle, and you told me 180 degrees. Okay, how did you know that? Okay, you didn't measure it, you just heard it so often. You know, a straight line, the angle from point to point to point, that's 180. That's in your memory banks from way long ago, and you never question it. Do you see how that is so much better to be at 180? What if the two cats here and here? Okay, they're equally close to me as they were, but boy, that is a bad angle. And if they were really my two cats, when they hate each other, they don't really fight, they bop each other on the head. They pull their claws in and whack them on the head. Okay, cats are weird, I love watching them. So anyway, that would be a bad angle. Linear is great. And bond angle. Now, there's a little bit more. And I'm taking you on a side trip. Remember when you started chapter 7, we talked about types of bonding. And we had two major types. Ionic, where we had a complete transfer of electrons. And what was that second one called? Covalent. Okay, now, this is sharing. There's actually two ways to share. And there's something called polar covalent and nonpolar covalent. Okay, let me illustrate with an idea. There's two ways to share. When I was growing up, I had a younger sister. Okay, I lie now. I don't say she's younger. I just say we're the same age. But anyway, when I was growing up, I had this younger sister. There was a rule in our house that we had to share our toys. I was older, I was bigger, I was meaner than she has ever thought of being. And so those toys spent about 90% of the time in my room, 10% of the time in her room. We were sharing, but that's unequal sharing. Okay, now on the other hand, what if she'd been my twin? Same age, same size, same degree of meanness. Okay? I bet we would have shared those toys 50-50. So we have two ways of sharing, and one is called polar covalent, and this is unequal sharing. And nonpolar covalent is the equal sharing. Now, I'm taking a side trip from this beryllium chloride for a little bit. When I teach about polarity, it's probably the most sophisticated or difficult thing we have. Let's go back to a couple of molecules here. In fact, let's go to 3. Okay, when we have sodium chloride, we know it's ionic. Big jump across. Full positive charge, full negative charge, end of story. Okay, now let's take HCl and look at it a little bit better. Remember how I said a generalization last week? 99% of hydrogen compounds will be covalent. So if I do the Lewis dot structure for HCl, it would be looking like this. Okay, now, electronegativity is going to creep into the picture. Remember how we reviewed where hydrogen belongs in electronegativity? Who is more electronegative? Hydrogen or chlorine? Who's closer to the hot spot of fluorine? Chlorine. Okay, chlorine is greedier for electrons than is hydrogen. Bigger, older, meaner sister. These electrons actually shift over. It's not a total giveaway, so it's not ionic, but they shift over toward the more electronegative side. And there's two ways people show this. You can show it with an arrow, like a vector, to show which way they shifted to the more electronegative side. Those electrons spend about 90% of their time close to this nucleus and about 10% of their time close to this nucleus. An alternative way of showing that small Greek letter delta means partial charge. So this side of the molecule takes on a partial negative charge, and this side then, because the electrons have shifted away from it, take on a partial positive charge. This and this are showing you the same sort of thing. This is referred to as polar covalent unequal sharing. Now, why is it called polar? Let's analyze the word. If you played with magnets as a child, you talked about the north pole and the south pole of a magnet. Okay, you're saying the north side, the south side. This is the partially negative side or pole. This is the partial positive side or pole. So we say it's polar. Now, if we do the Lewis dot structure for this, you've got two like things. They have identical electronegativities. Here's you have the twin sisters. And so those are going to share equally. So this would be referred as non-polar covalent. And a lot of people just don't say the covalent because if you say polar or nonpolar, you're always referring to covalent. It's understood. Now, here's the hard part. And I want to go ahead and finish this little, even if I run us over just a tiny bit. What we're talking about, there's two levels, and this is the part that messes people up. I can talk about the polarity of a bond, okay? Or I can talk about the polarity of the whole molecule. So there's two levels to talk on. Let's go back from this side trip. Okay, we said beryllium chloride is linear from the Vesper theorem. Let's examine bond by bond. I have beryllium and I have chlorine. Who's more electronegative? Chlorine. That's a polar bond. Same story over here. Okay, so you got the idea of polar bonds. This is the hard part. If you have a molecule like this, okay, what if I stand right here and I ask two of you of absolutely equal strength? I'm going to have one of you stand here and grab my arm, and I'm going to have a second person equal strength now over here and grab my arm, and I say, pull as hard as you can. Do I move? No, because the forces cancel out. So here's the biggie. You got a molecule, linear. You have a force, you have a force. Equal and opposite. If you can visualize those will cancel each other out, then you got to tell me the molecule as a whole is non-polar. So you can have polar bonds all over the place, okay, but overall the molecule is non-polar. That column up there is the polarity of the whole molecule. So for this, we would say beryllium chloride is non-polar. Now, let's look at models here just real quickly. We have these kits, and I'm going to try to grab a bunch of these for you to use this next hour. How many of you need to do Lab 14 stuff? Quite a few of you? Okay, that's highest priority because 14 is due today. But the rest of you stay here and I'll try to get you toys. These are fantastic, but they're not worth the money. What you can do, and I'll let you use stuff on test day, gumdrops and toothpicks. When you have your central atom right here, this is beryllium, chlorine, fluorine. Force, force, cancels out, we say nonpolar. Now all you would have to do, let's say instead of having chlorine, you bring in fluorine. Okay, huge force, moderate force, polar bond, polar bond. What about overall, polar or nonpolar? It's polar because the forces don't cancel. I got the strongest guy in the room and the 90-pound weakling. Will I move? Oh yeah. From that way. So you got to see symmetry. And one more shape. If I can find the right tools here. Okay, here's what I want to show. Remember when we did BF3? BF3? And if we would fire through this stuff, we would have three things around the central atom. Okay, cat story. 3 cats love me, hate each other. Okay, and to a cat, front of the person, back of the person, doesn't make any difference. Okay, one cat's here. The second cat is really intelligent, but I don't have to say that, all cats are intelligent. Okay, so she knows when she comes to sit down, there is a third cat coming. Okay, should she sit right here? No, a little bit back. Where should the third cat sit? A little bit back. And the shape of our molecule, when you have 3 things around the central atom, 3 cats, spread it out. Trigonal planar is what this is called. Trigonal, because it's like a triangle. Planar, because it's flat. The Mercedes molecule. Okay, now, you've got boron, fluorine, fluorine, fluorine. Polar bond, polar bond, polar bond. Okay, now if you can see that those forces would cancel, you should tell me nonpolar overall. If you don't think they'll cancel, then you'd say polar. So let's hear it. Buy your freedom. Nonpolar.